In its final few days, Cassini embarked on a series of almost reckless orbital trajectories that were so risky to the spacecraft's safety they would never have dared to be attempted earlier in its mission. Taking the probe closer to the planet than ever before, the team flew Cassini repeatedly through the gaps between the upper atmosphere of the planet and the inner rings. Throughout September 2017, as it performed 22 of these perilous dives, Cassini was able to take measurements of the gravitational tug of both the planet and the rings. This data was then used to calculate the mass and density of the most substantial ring in the Saturnian system. The B ring makes up 80% of the mass of all the rings, and yet Cassini's measurements suggested that the total mass of the ring was surprisingly low. This result, although not conclusive, strongly points to the fact that the ring's origins lie not in the ancient past during the formation of the planet itself, but to a far more recent and dramatic event involving one of the worlds trapped in orbit around it. The rings, it seems, were born of a moon. Saturn has 62 large moons, and countless smaller ones, that range in size from planetary-scale objects like Titan to smaller, irregular lumps of rock like Aegeon. And we're still hunting for new moons to add to the list. On its travels, Cassini spotted 2 objects within the F-ring that are potential candidates for moonhood, but as yet S/2004S6 and S/2004S3 remain unverified and unconfirmed. Within this menagerie of worlds are an endless variety of clues written into the size, form, and surface features of the moons that allow us to read the history of the Saturnian system, revealing the often violent and volatile events in its past. Mimas is otherwise known as the Death Star moon, and was first spotted in 1789 by William Herschel, who is immortalized in Mimas's eponymous huge impact crater. Mimas is just 396 kilometers across, and the Herschel crater covers 130 kilometers of that surface, a deep scar that tells us that once, long ago, there was a giant impact that almost destroyed the moon. Iapetus, the third largest of Saturn's moons at 1,500 kilometers across, is almost planetary-sized and has a distinctive two-tone coloration, half light and half dark. Iapetus was discovered by Giovanni Cassini himself in 1671 and has another distinctive feature that we have long puzzled over. Running around 3/4 of the moon's diameter is a massive equatorial ridge. It's one of the highest mountain ranges in the solar system, 20 kilometers from the peaks to the ground below, and it's thought this may have formed because a ring that once circled the moon collapsed onto its surface. Hyperion is the strange sponge-like moon that tumbles around in Saturn's orbit, which in 1848 was the first non-spherical moon ever to be discovered. To this day, it remains a mystery as to what caused its punctured surface and irregular shape, and it's been suggested that Hyperion is in fact a remnant of another moon that broke up long ago. Pan, the small walnut-shaped moon that was discovered less than 30 years ago from the analysis of images taken by the Voyager 2 probe, is named after the Greek god of shepherds. It's so named because Pan is a shepherd moon, clearing the orbit of the Encke Gap, a 325-kilometer space within the A-ring. Its distinctive equatorial ridge is thought to be made of material that's been swept up and accumulated as it clears its path through the ring. Cassini's endless stream of images and data until 2017 has enabled scientists to analyze each of the moons in ever more detail, and it's become increasingly apparent that they are intimately linked with the ring system they orbit. Many of the moons are made of exactly the same material as the rings themselves. Mimas, Iapetus, and Hyperion are ice moons, composed almost entirely of frozen water ice, with only the smallest amounts of rock in their makeup. From the evidence that we've been able to read on their surfaces, it seems almost certain that through 4 billion years of violent interactions, at least some of the moons of Saturn must have both come and gone over the planet's history. All of this begins to point us towards the idea that perhaps the most intriguing moon in Saturn's long history is one that is now entirely missing. Around 200 million years ago, as dinosaurs roamed the Earth, we now believe a long-lost moon orbited close to the planet Saturn, a moon perhaps 400 kilometers across and formed almost entirely of ice. This was a doomed world, orbiting too close to resist the immense pull of Saturn's gravity, its fate sealed at the moment of its birth. It was the French astronomer and mathematician Edouard Roche who first suggested the existence of this long-lost moon in 1848. He christened it Veritas, after the Roman goddess of truth, who according to legend is supposed to have hidden in the bottom of a holy well. Roche had postulated the existence of this moon while exploring a particular dynamic of celestial mechanics that describes the potentially violent gravitational relationship between two celestial bodies. He was able to demonstrate that when a moon moves within a certain distance of the planet it is orbiting, it can cross a threshold where the force of gravity is so strong, the moon will be ripped apart. This distance has become known as the Roche limit, and is dependent on many factors, including the mass, radius, and physical characteristics of the moon and planet. Outside of the Roche limit, a moon can exist in happy equilibrium with its planet, orbiting in the gravitational grip of the larger body while maintaining its physical integrity. But if that same moon's orbit degrades to the point where the Roche limit is crossed, the tidal forces exerted on the moon exceed the gravitational attraction that holds the moon together in a sphere, resulting in the moon's destruction. This relationship applies to any moon-planet system, including our own. Here on Earth, we see the relationship between our planet and moon on a twice-daily basis as the tides ebb and flow across the planet. These tides are caused by the difference in the gravitational pull of the moon from one side of the Earth to the other, and that difference, although subtle, is powerful enough to move entire oceans with the forces of tidal gravity. Just as the moon creates tides on Earth, so the Earth also has a tidal effect on the moon, and because the Earth is much greater in mass, that effect is more powerful than you might think. The Earth's pull is in fact powerful enough to deform the moon's surface. Even today it causes moon tides on the lunar surface where it causes the rock to rise and fall. But the effect was even stronger 4 billion years ago, when the moon was nearly 17 times closer to the Earth. Back then, the pull from our planet caused a tide of solid rock to rise and fall by many meters, and if the moon had ever come any nearer, it would have crossed the Roche limit and been ripped apart. When Edouard Roche first formulated the equations calculating this line, he realized that the result of such destruction would not just be the obliteration of a moon, but also the creation of millions upon millions of fragments, the debris of the moon orbiting around its destroyer. He also deduced that in time these fragments would form once again into the most delicate of structures, a system of rings, under the influence of the planet's gravity. In one of the more gruesome tales from classical mythology, Saturn, the Roman god of time and harvest, actually ate 5 of his newborn babies to prevent them taking his power. Now, Cassini has shown us that, at least metaphorically speaking, they weren't far wrong. We now think that 10 to 100 million years ago, just beyond the outer reaches of Saturn's vast atmosphere, an icy moon orbited, gradually edging closer and closer to that tipping point, the Roche limit. As Saturn's immense gravitational force pulled at it, this great moon began to rupture, and in a moment undoubtedly worthy of even the greatest of mythological stories, up to 30 million trillion tons of ice, more than 30,000 times the weight of Mount Everest, broke apart in orbit and spread out around Saturn. Travelling at tremendous speed around the planet, it's likely that this debris quickly scattered to encircle the giant planet, and in the space of no more than a few days, Saturn's iconic rings had been born. Today, this giant ring system has evolved into the intricate structures we can see in the night sky. Saturn's powerful gravity has helped keep its near-perfect elliptical shape, but an endless series of collisions have caused it to gradually flatten out. Now this debris forms a disk wider than Jupiter, yet on average just 10 meters thick. With moon-sized chunks of ice orbiting through this structure, great voids have been cleared, turning one ring into many. In places, moons have pulled particles of ice upwards to create strange peaks over a kilometre high, which cast spectacular shadows across the rings. Saturn, once a tiny world of rock and ice, a world that has undergone repeated transformations, has today become the solar system's greatest jewel. And Cassini, our most intrepid of explorers, has forever deepened our understanding of the life story of this planet. Yet perhaps Cassini's greatest gift is not in its revelations of the past, but in the glimpse it has given us of the future. Because just beyond Saturn's rings, Cassini would discover a hidden treasure, a world that may hold answers to some of our deepest questions about our place not just in the solar system, but in the universe. One of the unmistakable jewels of the Saturnian system is Titan. A giant, it is the second largest moon in the solar system, and this planet-sized satellite is larger than the smallest planet Mercury, and 50% bigger than our own solitary moon. Discovered by Dutch astronomer Christian Huygens in 1655, it has held its secrets close for centuries, cloaked by thick clouds. The only moon in the solar system with a dense, distinct atmosphere of its own, from afar Titan hinted at being far more like a planet than a moon. It would take a mission of breathtaking ambition to finally peer under her veil and see the wonders that lay beneath. On Christmas Day 2004, after a 7-year journey across the solar system, the Cassini probe released its sibling craft Huygens, setting it off on a 4 million kilometre path to Titan. Simple in appearance, Huygens looked as if it had borrowed its design from the classic cartoon UFOs of the 1950s. But nothing was simple about Huygens. This was a highly advanced spacecraft about to begin one of the most complex maneuvers ever attempted in the history of human space exploration. As it made its 3-week journey towards Titan, the team of ESA, European Space Agency, scientists who had dedicated a lifetime's work to the project, watched on, hopeful but helpless. From the moment of release, they had lost direct control of the probe and were unable to send it commands. Instead, as planned in the mission protocol, Huygens was now entirely controlled by the onboard autonomous computer systems. All they could do was watch and wait, to see if Huygens could fulfill their ambitions by becoming the first probe to land in the outer solar system, on a moon other than our own, in the most distant landing of any spacecraft. To succeed, Huygens would have to execute a perfectly controlled landing protocol designed to use Titan's atmosphere as an aerobrake, before employing a parachute system to deliver the scientific instrumentation to the surface. And all after awakening itself from a 6.7-year intergalactic sleep. The probe had remained in an entirely dormant mode, except for a 6-monthly self-health check, and only at the point of separation from Cassini was the timer set to wake the probe up, 15 minutes before entering the atmosphere of Titan. The proposed landing site for Huygens also held much uncertainty, chosen to be in the southern hemisphere of Titan, 192.3 degrees west, 10.3 degrees south to be precise. The area was surveyed by Cassini's cameras from an altitude of 12,000 kilometers, and appeared to be near a site that had many of the characteristics of a shoreline. Landing into an extraterrestrial ocean had been part of Huygens' original design, so in theory the craft was expected to survive any splashdown into a liquid surface on Titan. On the 14th of January 2005, the 318-kilogram probe entered Titan's atmosphere, 1,270 kilometers above the surface, and began its descent protocol. On-board accelerometers monitored the craft's deceleration, waiting for the precise moment to trigger the explosive bolts that would blow off the front heat shield and back cover, and release the pilot parachute, which would then pull out the main parachute, slowing the 2.7-meter wide craft from its nearly 2,000 km/h descent and allowing it to drift safely to the surface. All of this would need to play out perfectly, while more than 1 billion kilometers away, a group of nervous humans sat in near silence in mission control, waiting for the first telemetry to confirm that Huygens was safely on the ground. Every second was utterly critical, because Huygens had no more than 3 hours of battery life, and with an expected 150-minute descent, that meant not much more than half an hour's activity on the ground. For a mission that had cost millions of dollars and taken decades to plan and execute, its success would depend on this incredibly short window of exploration. Despite its sophistication, Huygens could not communicate directly in any detail with Earth. Instead, all of its detailed telemetry would need to be relayed back to Earth via Cassini's communications system. This meant very little was known about the probe's status during the 2-hour and 27-minute descent. But at precisely 11:38 UTC, the Robert C. Byrd Greenbank telescope in West Virginia picked up the weakest of carrier signals generated by Huygens' 10-watt internal transmitter to confirm that Huygens had arrived safely on the surface. This extraordinary probe was now alive and active on an alien moon orbiting Saturn. Just under 5 hours later, the Cassini probe orbiting far above the moon's surface began relaying the precious data from Huygens back to Earth. And by 1945 that evening, the first extraordinary picture was released, showing a view from Huygens about 16 kilometers above the fast-approaching surface. This was space exploration on an awesome scale. A photograph taken by a tiny space probe floating down on a parachute to the surface of a moon, orbiting a planet over 1 billion kilometers from Earth. It's instantly apparent that this is no featureless rock. The channels running across this picture are recognizable as the geology of a world shaped by liquid, covered in drainage channels crossing the landscape into what looks like a lake bed or sea. And more was to rapidly follow. Just a few minutes later, the first image from the surface arrived on Earth. The first view of the surface of a world in the frozen, far reaches of the solar system. It's an image that is worthy of the very closest of inspection, because, as always in science, the more you know about it, the more wonderful it gets. What we can see in this extraordinary image is something that is exactly like a floodplain or riverbed here on Earth. We can say this with some certainty because you can see that the rocks are abraded. They've been smoothed by the action of a liquid flowing over them. But there are no rocks. Huygens was able to confirm that these are in fact boulders of frozen water ice, sculpted on the freezing temperatures of Titan's surface. These rocks of ice are sitting on a surface that, as one Huygens scientist described it, is like snow that has been frozen on top. If you walk carefully, you can walk as on a solid surface, but if you step on the snow a little too hard, you break in very deeply. So if the temperature is so cold on Titan that rocks are made from water, what liquid is flowing over the rocks of ice carving the riverbeds and floodplains? We'd known for some time from spectroscopy carried out here on Earth that Titan had an atmosphere rich in methane gas. And many scientists had wondered if this could mean that liquid methane existed on the surface. But it was only when Huygens was actually on the surface and its instruments began testing the atmosphere directly that we could begin to see just how alien this world was. For an unexpectedly long 70-minute period, Huygens was active on the surface, detecting significant amounts of methane in the air. Huygens was also able to confirm that the surface temperature on Titan was a freezing -180 degrees Celsius, combined with an atmospheric pressure equivalent to 1.4 atmospheres here on Earth. The measurements confirmed that on Titan, methane was not a flammable gas, but potentially in abundance on the surface, in liquid form. Titan, it seemed, was a wet world, not with flowing water, but with liquid methane driving ice-like rocks down mountain channels and out into open floodplains. But despite early speculation, Huygens had not made a splash landing. It lay in a dry riverbed, and after surviving for just a few hours, its battery ran dead. This miraculous explorer switched off without directly detecting liquid methane on the surface. It would be 2 years later, as Huygens lay frozen and dead on the surface of the Moon, that the very much alive Cassini probe would fly high above the south pole of Titan and beam back an image that would provide a unique view seen nowhere else in the solar system beyond Earth. This was our first glimpse of liquid on the surface of an alien world. A lake composed of methane, ethane, and propane near the south pole of Titan. Named after one of the Great Lakes of North America, Ontario Lacus is like nothing we have ever seen on Earth. A 15,000 square kilometre lake of hydrocarbons, whipped by winds that are clearly eroding the shoreline. And Ontario Lacus was just the first. Today, thanks to Cassini's years of observation and photography, we have discovered more than 40 lakes of liquid methane, including Ligeia Mare, a vast body of liquid hydrocarbons with a shoreline over 200 kilometres in length. We've seen mysterious bubbles rising from its depths. Kraken Mare is the largest known body of liquid we have so far found on the surface of Titan. This hydrocarbon sea covers an area of 400,000 square kilometres, 5 times larger than Lake Superior, and has a depth that we suspect descends to 160 meters. We've seen waves in this sea, and islands and currents, endlessly being filled by the flash floods of methane rain that we are certain fall on the highlands surrounding the sea, feeding the rivers and streams that flow into it. Earth, it seems, has a strange cold twin, a moon, not a planet, that is millions of miles away, where lakes are liquid methane and mountains are made from frozen water ice, as hard as rock. What's also fascinating and tantalizing is that Titan has a complex chemistry, a carbon chemistry, the chemistry of life. We have found molecules like hydrogen cyanide, which are the building blocks of amino acids, molecules like vinyl cyanide, which chemists and biologists speculate could form some sort of cell membrane. In fact, all of the ingredients for life are present on the surface of Titan today. That doesn't mean there is life. In reality, very few scientists think there will be life on Titan today, as it is, after all, minus 180 degrees Celsius at the surface. But with a little heat, it might be a very different story. In a few billion years' time, as the light of the dying sun reaches out beyond the inner solar system to touch the outer reaches with its warmth for the very first time, Titan will begin to warm. Its mountains of ice will shrink and melt, and the frozen water they contain will replace the liquid methane, which will have evaporated away into space. Mountains will become oceans, and in a strange twist of fate, at the end of the life of our star, perhaps the solar system's last water world will be born. David Grinspoon believes it's a prediction we cannot rule out. Titan today has all these juicy organics pooled and lying on its surface, and yet it's so cold and so dry that it may be that nothing is really happening biologically there. But we can imagine a time in the far future when the sun has heated up to the point where the inner solar system has become uninhabitable, where Titan may become quite habitable. That methane greenhouse will become more powerful as the sun gets hotter, and at some point that icy crust will start to melt, and you'll have large pools of liquid water on the surface full of all those complex organic chemicals, and that is a recipe for the kind of place where the origin of life can happen. So even if Titan doesn't have life today, and that's something we still have to search for, there's every reason to imagine that at some point in the future, it could be a great place for biology. It's easy to think of habitability as a permanent feature of worlds, a defining characteristic, if you like. Earth is habitable because it's in the Goldilocks zone around the sun, not too close and not too far away. But it's more complicated than that. Solar systems are dynamic places. Over long timescales, planets change orbits and their parent stars evolve, and worlds that were once heaven can become hell. We now understand that Earth has been a fortunate world, an oasis in a constantly changing solar system that's maintained a stable climate, perhaps against the odds. For the 4 billion years it's taken complex living things to evolve. We don't know how many planets like Earth are out there amongst the stars, where the ingredients of solar systems have assembled into structures capable of dreaming of other worlds. But we must consider the possibility that there are very few, and that would make Earth, and us, extremely rare and precious. Nearly 1 billion miles from the warmth of the Sun, on the outer edge of Saturn's rings, lies the icy moon of Enceladus. A small moon, about the size of Iceland, Enceladus is the most reflective object in the solar system. Over 90% of the light that hits it bounces back. That's because the surface of this ice-covered moon is covered by crevasses just like we see on the surface of glaciers here on Earth. But on Enceladus, these cracks in the ice occur on a much grander scale, with some stretching for over 100 kilometers. But for all that's going on the surface, it's what we discovered beneath Enceladus's shell of ice that must rank as one of the greatest surprises in 21st century space exploration. A surprise that had been hiding in plain sight for decades. The first photograph of Enceladus was taken by Voyager 1 in 1980. It was actually captured unintentionally, a moon photobombing the planet, and nobody even noticed Enceladus until over 35 years later. But when the image was eventually enhanced, a remarkable feature, no more than a misty blob, began to emerge on one side of the moon. 24 years later, Cassini saw exactly the same thing, but this time in much more detail. As Cassini approached Enceladus, the anomaly revealed itself. Giant plumes of water vapor and ice were erupting from its surface. Over 200 kilograms of material was being released every second, feeding one of Saturn's outer rings and helping to replenish it. These discoveries inspired the Cassini team to take an audacious risk. Piloted from nearly 1 billion miles away, Cassini was guided dangerously close to the plumes and, using its cosmic dust analyzer, was able to actually touch the plumes of ice and collect a sample from one of the eruptions. As Michel Doherty, scientific leader on the Cassini project, explained, the really close flyby that we had of Enceladus, where we were 25 kilometers above the surface, is probably closer than any spacecraft has been to a planetary body before. And the Cassini mission team said they'd never do it again because we were in the atmosphere, well, in the plume, which was really dense. They didn't lose control of the spacecraft, but they felt they might, because the mag boom used to stickle from the side of the spacecraft, and that almost started tumbling the spacecraft. What the scientists discovered, though, thanks to this and a series of similar flybys, was breathtaking. The plumes were spewing out of fissures known as tiger stripes, being projected from deep within this ice world, rising up from an ocean of salty liquid water beneath the ice. How could such an ocean exist in the far frozen reaches of the solar system? The answer lies once again in the power of Saturn to control the destiny of the moons in its dominion. Unlike the long-lost moon of Veritas that was destroyed by the might of Saturn to create its rings, in the case of Enceladus, its mother planet has breathed life, not death, into its structure. Enceladus orbits Saturn, and the planet's vast gravitational force pulls at the moon, holding it in orbit. But every couple of rotations, another larger moon called Dione aligns with Enceladus, drawing it back. This repeated tug of opposing tidal forces stretches and squeezes the moon, warming its core and melting its icy interior. Exactly the same gravitational forces that destroyed one of Saturn's moons are now breathing life into another. But it's what Cassini found in the chemical makeup of the plumes that changed everything, because as it analyzed the columns of water, it discovered complex organic compounds and silica particles, direct evidence that deep below the ice at the bottom of a salty ocean of water, there were hot hydrothermal vents, exactly like the ones from which we believe life emerged on Earth almost 4 billion years ago. Out in the frozen outer reaches of the solar system, Cassini has given us a glimpse of the world beneath the ice on Enceladus and revealed a warm, watery oasis, a world in which it really is possible that life could exist. Exciting though the prospect of life in space is, if it is out there on Enceladus, it's likely only to be home to the simplest and most primitive organisms, and given how violent and changeable Saturn's past has been, this world may have arisen relatively recently. We don't know how long Enceladus has been active, but if it's only tens or even hundreds of millions of years, that might not have been enough time for life to get going. And despite all the caveats, the very fact that the Saturnian system holds the potential to host life is a truly remarkable discovery, and one that compels us to explore even more. But for Cassini, the brave new world under the ice of Enceladus was a bittersweet discovery. 13 years after it arrived in orbit around Saturn, as Cassini's fuel finally began to run dry, the team at NASA realized it couldn't risk letting this probe crash land on Enceladus and contaminate a potential habitat for life. As Carl Murray explains, because we now knew Enceladus was a potentially habitable environment, we couldn't risk Cassini crashing into it or coming near it because there might be microbes hitchhiking on the spacecraft, and we couldn't allow contamination of Enceladus. So we consciously picked an end of mission that would use up its fuel and then send the spacecraft into the giant planet itself. We journeyed out across space to Saturn to see this great beauty up close, but in the end we were rewarded with insights that hit far closer to home. As is so often the case in exploration and science, the real treasure was found in the unexpected shadows. On this mission, it was in the shadow of the rings, because there we found a tiny world with the potential to harbour life, to provide reassurance that for the first time, we might not be alone. Would such a discovery matter? Yes, it would. At this moment in history, we are, I think, in need of reassurance, or perhaps a reminder, that there is great beauty and knowledge and perhaps even life and meaning beyond our shores. We will, I'm sure, go back to Saturn and its moons, explore deeper, stay longer, and maybe one day even visit there ourselves. We don't yet know what we will discover, but we can be sure it's a story that has only just begun. Cassini's discoveries have profoundly changed our understanding of the Saturn system, from the planet itself to detailed structure in the rings. We now know what the surface of Titan looks like, and we have also pierced through that haze with the radar to map it all out. The lakes and seas are liquid methane on the surface of this moon. And then, of course, the big discovery of geysers coming out of the south pole of Enceladus, flying through those geysers, sampling, tasting, measuring what's coming out, the gases and the particles, and finding not only do you have a lot of water from that liquid water ocean, but you have organics. You have nitrogen, you have methane also. So you have sort of the key ingredients: carbon, hydrogen, oxygen, nitrogen, the building blocks for life. It's so intriguing to find a moon that's only 500 kilometers across with a liquid water ocean, just one of a suite of ocean worlds in our solar system. And perhaps life is just next door. The reason we find it so tough to leave the Earth is because of the mass of the planet, all 5.9 sextillion tons of it, which creates a gravitational pull so strong it requires an escape velocity of around 11.186 kilometers per second to make it off the Earth and into space. That's a lot of speed to counteract the 9.8 meters per second squared of gravitational force that is continually tugging us down. Gravity keeps our species firmly locked to the surface of the planet, but it also keeps a tight grip on everything else on the surface of the Earth, be it solid, liquid, or gas, including the 5.5 quadrillion tons of nitrogen, oxygen, carbon dioxide, and other trace gases that together make up the Earth's atmosphere. In the very simplest terms, the size of the atmosphere of any planet is intricately linked with the mass of that planet, The bigger the mass of a planet, the greater the attraction of gases to its surface. But that's not the end of the story. The ability of a planet to retain an atmosphere is also dependent on a multitude of other factors, including the composition of the atmosphere, its temperature, proximity to the Sun, geological activity, the ability of the planet to protect itself from the ravages of the solar wind, and finally the impact of life itself, which has seen our atmosphere gradually pumped full of oxygen. It's the intricate balance of these factors that dictates the endurance and composition of the gases around a planet, each one a unique atmospheric fingerprint. Fast forward through the history of the solar system, and we see a familiar theme again and again around the inner rocky planets. Each of the 4 planets grabbed onto a thin atmosphere, but then the individual characteristics of each planet set in motion its own individual evolution. Saturn is a gas giant, alive with storms of unimaginable ferocity, a world of alien weather where diamonds rain down from the sky, and bubbling vortexes whip around the planet so fast they catch up with their own tails. And glistening in the distant light of the sun is a 500,000-mile ring of almost pure frozen water, broken into millions of individual pieces. This structure is unique in our solar system, sculpted by the delicate hand of gravity. Yet for all of their iconic beauty, the rings are just a fleeting shadow, an echo of Saturn's past, and an ephemeral structure that has adorned the planet for a brief moment in its history and will soon disappear again. Saturn is a place of many worlds, encircled by at least 62 moons. This menagerie of satellites boasts worlds of astonishing variety. Titan, bigger than the planet Mercury, is the only moon in the solar system to have its own substantial atmosphere, while Mimas is the smallest body in the solar system. Perhaps most astonishing of all, though, is Enceladus, an ice moon with an ocean of liquid water inside that seems to contain all the building blocks of life. Composed of 96% hydrogen and 3% helium, Saturn has a diameter at its equator almost 10 times the size of the Earth, at 120,536 kilometers. Its volume would hold 800 Earths. However, with a mass made up predominantly of gas, the planet's density is remarkably low. As the only planet in the solar system less dense than water, if you could find a bathtub big enough to hold it, Saturn would literally float in it. Beneath the frosty minus 178 degrees Celsius cloud tops, the pressure rapidly increases under the huge weight of Saturn's dense atmosphere. The hydrogen gas of the upper layers turns at first into liquid, and then, hundreds of kilometers further below the planet's cloud tops, into slushy metallic oceans of hydrogen. We can only make an educated guess about the structures that lie within Saturn's unreachable core. With temperatures at its center exceeding 11,000 degrees Celsius, Saturn generates far more heat from within itself than it receives from a sun that sits on average 1.4 billion kilometers away, meaning that it must be generating its own heat. With such extreme temperatures and pressures, the structural makeup of this planet is uncertain and hotly debated. According to planetary scientist and physicist Jonathan Lenine, if you go down, down, down through the hydrogen, through the helium rain to this core of rocky and icy material, it's not rock and ice. It's some sort of atomic crystal where the elements of rocks and ice, the silicon, the oxygen, the magnesium, are all together in a structure that doesn't exist in the rocks on the Earth. Now, in the case of Jupiter, it might actually be warm enough that the core is a liquid, that it's molten. In the case of Saturn, it's probably a solid core, but definitely an exotic one. Undoubtedly, there is a dense core at the heart of Saturn, one that is almost certainly composed of iron-nickel alloy and rocky silicon-based compounds. But exactly how this material behaves at such extremes remains a mystery. From its surface all the way down to its center, Saturn is a world of mystery. This gas giant, along with its sister planet Jupiter, is worlds apart in character from Mercury, Venus, Earth and Mars, the terrestrial planets of the inner solar system. It's hard to imagine how they could all have been created from the same ingredients, the singular cloud of gas and dust that gave birth to every planet in our solar system. But if we go back far enough in time, we begin to uncover a history with a surprisingly familiar origin. The beginning of Saturn's story is far more recognizable than its present-day character would suggest, because at the heart of all the ringed planet's beauty lies a lost world, a primordial one that disappeared from view billions of years ago, and yet was the seed for everything that Saturn was to become. Without this early world, there would have been no gas giant, no rings of ice, and no hope of an orbiting oasis of life in the far distant reaches of our solar system. The story of Saturn, like that of all the planets, began around 4.5 billion years ago. In the light of the awakening sun, a vast cloud of gas and dust swirled around our newly formed star, and that protoplanetary disk of gas and dust clumped and coalesced until it slowly began to form into a collection of embryonic worlds that would go on to become the 4 rocky planets sitting closest to the sun. Millions of kilometers further out, in the cold, distant reaches of the solar system, a similar story was playing out, but this tale of planetary formation would follow a very different path. That's because Saturn was molded beyond a boundary called the ice line, sometimes also called the snow line, which is a frontier that marks the divide between the terrestrial planets and the gas giants. Respective proximity to this line would lead the evolution of Saturn and that of its neighboring planet Jupiter to play out very differently. The ice line, as you might expect from the name, is a way of dividing a solar system into 2 broad zones based on temperature. Inside the ice line, the strength of a star is strong enough to keep things pretty warm. But step onto the other side of the line, and you've crossed a boundary where it becomes cold enough for volatile compounds like water, methane, ammonia and carbon dioxide to condense and freeze solid. Each of these compounds does, of course, have its own precise ice line due to the different specific freezing points of each individual compound. But beyond a certain point, the boundary begins to incorporate the freezing points of a large number of compounds. Today, the ice line is thought to be around 5 AU. That's around 750 million kilometers from the Sun, which means it lies well beyond the asteroid belt, at a distance just before the orbit of Jupiter. But in the infant days of the solar system, that distance would have been much less. With a weak young sun shrouded in an opaque cloud of dust and gas, the early ice line would have fallen about 2.7 AU from the Sun, smack bang in the middle of where we find the asteroid belt today. We know this because we've been able to explore the makeup of the asteroids on either side of this line. Beyond the 2.7 AU line, we've discovered the asteroids to be icy objects with large amounts of water ice locked away within them, while on the inside of this line, we find a very different class of asteroid, dry and largely devoid of water. It seems these bodies formed in a region of space that was simply too warm to allow substantial amounts of ice to exist. Why does the ice line matter in the story of Saturn's evolution? In the early solar system, as the protoplanetary disk swirled around the young sun, the ice line not only defined an important boundary in terms of temperature, but it also created a dramatic difference in the abundance of material available to build a planet on either side of the line. Beyond the ice line, the lower temperatures meant that all of those frozen volatile compounds were swirling around in the cloud of gas as solid grains, building blocks that provided vast amounts of additional material to feed into the process of planetary accretion. And the impact of this simple physical difference was profound. On our side of the line, we find only rocky planets like Earth, Venus and Mars, while on the other side of the line, there is not a single planet that we recognize as terrestrial, just the gas giants of Saturn and Jupiter and the ice giants of Uranus and Neptune beyond. To understand the reason for this stark delineation, we need to look back to a critical time in Saturn's history, to the moment where the paths of the planets either side of this ice line began to diverge. Saturn began its life not as a beautiful jewel, but as a tiny, ugly, ragged world. Just like its terrestrial cousins, the origins of this gas giant planet began with the clumping together of tiny specks of gas and dust that slowly grew into bigger and bigger clusters. As this embryonic new world tumbled wildly through space, days would have lasted minutes as the distant sun lit its twisted surface, rising and falling in chaotic rhythm repeatedly. Eventually, as it grew, this ragged rock began to transform itself, taking the new shape of a spherical world as it went from planetesimal to protoplanet. On the warm side of the ice line, the growth of the terrestrial planets came to an abrupt halt. As these planets had secured stable orbits and began clearing their way through the protoplanetary disk, the supply of raw ingredients ran dry, and so their growth simply stopped, starting with the runt of the litter Mars, followed by Venus, and then our planet Earth, the largest of the rocky planets. But on the other side of the ice line, it was a very different story. With no shortage of building material, the growth of the protoplanetary Saturn was able to progress at a rapid rate. With abundant amounts of rock and ice, the young Saturn continued to grow, quickly dwarfing any of the terrestrial planets that were forming in the far distant glow of the warming sun. Over a relatively short period of hundreds of thousands of years, this plentiful supply of material smashed and clumped and grew until, through a series of planetary-scale collisions, Saturn became the largest object for millions of miles in any direction. The bigger it got, the stronger its gravitational field grew, and so it could attract ever more material into its grasp. Eventually, the violence of its early life allowed Saturn to grow into one of the biggest worlds of rock and ice the solar system had ever seen. What did this world look like? We simply do not know. The detail of how any of the planets formed in the solar system is only sparingly understood. These are events that happened 4.5 billion years ago, and it's very much still cutting-edge scientific research trying to piece together the barest of timelines, let alone the intricate details of these distant events. Much of what we do understand of the evolution of our own solar system and the planets within it has been supported by our recent ability to study worlds outside it in neighboring systems. The study of exoplanets has allowed us for the first time to peer into the evolution of other star systems and witness the formation of hundreds of different planets rather than the 8 in our own backyard. Much of this evidence supports the idea that Saturn was once a world of rock and ice, a world that grew to perhaps 10 or even 20 times the mass of the Earth as it gorged itself on the available matter. This was a world we would at least have vaguely recognized, a place it is almost possible to imagine, a world that you could stand on and survey. But it was a world that wouldn't last. The fact that Saturn grew to such a size had significance beyond just scale. Its size pushed the planet towards a very different evolution, changing its relationship with the environment and ultimately sending it on a completely new path. It's because of its immense mass and its place in the solar system that Saturn wouldn't remain a rocky world for long. The history of the exploration of Saturn is littered with many of the greatest names in the field of science. Galileo Galilei was the first to peer at her through a telescope in 1610, mistaking the faint outline of the rings for 2 moons on either side of the planet. He famously reported the planet appeared to have ears. 2 years later, however, when he looked up again, the peculiar structures on either side of the planet had disappeared. We now know this is because the rings were facing the Earth edge-on at the time of observation. But for Galileo, this was a strange and mysterious anomaly. It would take almost 50 years and the more powerful telescope technology of Christian Huygens to solve the problem. Using a 50mm refracting telescope, Huygens was the first to spot a moon of Saturn, publishing his discovery of Titan in 1656. At the same time, his observations led him to begin formulating a theory to explain the strange ears that Galileo had first seen. Not moons, but a ring around the planet. Uncertain that he had enough proof to convince the scientific community of his hypothesis, Huygens did what was common at the time. He published his thinking not as a preliminary hypothesis, or even as a line of investigation, but instead, in order to mark the territory and protect his reputation, he announced his discovery in the form of an anagram. A C C C C C D E E E E E G H I L L L L M M N N N N N N N N N O O O O P P Q R R S T T T T T U U U U U. For 2 years the anagram remained unbroken, protecting Huygens' claim to be the first to identify the rings, while also giving him enough time to build the evidence to make the hypothesis defendable. It wasn't until 1658 that Huygens revealed the meaning of the anagram to be a Latin sentence: Annulo cingitur tenui, plano, nusquam cohaerente ad eclipticam inclinato, which means, it is surrounded by a ring, thin and flat, never touching, oblique in relation to the ecliptic. With the rearrangement of 62 letters, one of the most beautiful structures in the solar system, the rings of Saturn, had been revealed to the world, if not yet understood. While Giovanni Cassini and William Herschel went on to discover more moons of Saturn and to detail structures within the rings, including the 4,800-kilometer gap between the A and B ring that would later become known as the Cassini division, we still imagined the rings as one great disk, a flat, solid circle of material encircling the planet within. It was Pierre-Simon Laplace, the French Newton, who was the first to suggest in 1787 that such a singular structure around a planet would be unstable, and instead was more likely to be comprised of a number of solid ringlets. By the mid-19th century, it was the turn of the great mind of James Clerk Maxwell to investigate the rings. Unpicking centuries of conjecture around the nature of the rings, he demonstrated for the first time through a series of mathematical proofs that any solid structure, be it single ring or ringlets, would be unstable and so unable to exist around the distant planet. Therefore, Maxwell concluded, the rings must be composed of a huge number of small particles, all orbiting the planet independently. In his words, every particle of the ring is now to be regarded as a satellite of Saturn, disturbed by the attraction of a ring of satellites at the same mean distance from the planet, each of which, however, is subject to slight displacements. The mutual action of the parts of the ring will be so small compared with the attraction of the planet that no part of the ring can ever cease to move round Saturn as a satellite. With Maxwell's publication on the stability of the motion of Saturn's rings in 1859, our modern understanding of this distinctive feature of Saturn had begun. But it would be another 120 years before we'd get the chance to explore the most remarkable bodies in the heavens, as Maxwell described them, up close. At 14:26 Universal Time on the 1st of September 1979, after a 6-year journey from Cape Canaveral across over 1 billion kilometers of space, the Pioneer 11 spacecraft took us within touching distance of the rings of Saturn for the very first time. As our first explorer to cross the boundary of the rings, Pioneer flew across the ring plane beyond the outer ring, enabling it to photograph the Saturnian system in extraordinary detail, sending back a series of images that revealed the ringed planet in greater resolution than we could ever have seen from Earth-bound observations. On its way through the ring plane, Pioneer was able to take the first close-up measurements of the rings, and in doing so discovered not only a new ring system, the F ring, but also 2 new moons of Saturn. In fact, the spacecraft flew so close to the as-then unknown moon, passing at a distance of just 6,676 kilometers, it was lucky the mission didn't abruptly end with a massive collision. We now know Pioneer had encountered either Epimetheus or Janus, but we're still not sure which one of these 2 similar-sized moons it was, as both sit in the same orbit around Saturn. Traveling at a speed of 114,100 kilometers per hour, Pioneer passed within 21,000 kilometers of Saturn's cloud tops, making its closest encounter at 1629 UST on that September day, before speeding off beyond the rings and onwards on its journey to the outer solar system. As well as taking 440 images of the Saturnian system, Pioneer measured the characteristics of Saturn directly, An array of sensors were able to confirm that this giant planet was a bitterly cold world, with an average overall temperature of minus 180 degrees Celsius, and a composition made up almost entirely of liquid hydrogen. But beyond the basic data, perhaps Pioneer's greatest achievement was to plot a course through the Saturnian system and make its way safely through the ring system while returning data back to Earth. Now the stage was set for the 2 Voyager probes, already well on their way across space, speeding towards the ringed planet equipped with an even more advanced array of technology, ready to probe even deeper into Saturn's mysteries. The rings were named essentially in order of discovery. In terms of the main rings, it starts at the outermost, which is the A ring, and then goes into B ring, where most of the mass is. And there's a faint C ring and an even fainter D ring inside that. Then the E ring was discovered around 1980, when the rings as viewed from the Earth were edge-on. That's the one that's clearly associated with Enceladus. Then Pioneer 11 discovered the F ring, and then Voyager discovered the G ring. And the G ring, we know, is associated with a moon called Aegeon, which is the source material for the ring. At that stage, we stopped using the letters as a nomenclature. So there are other individual rings that have been named, but they tend to be rings or ringlets that are in the main ring system itself. Carl Murray, Cassini mission, on the organization of Saturn's rings. Just over a year after Pioneer had exited the Saturnian system, early in November 1980, Voyager 1 swept in with its high-definition cameras primed and ready for action. As it sped past Saturn at 17 kilometers per second, it was able to produce a wealth of new data about the planet, rings, and moons. One of its key discoveries was the identification of 3 new moons, Prometheus, Pandora, and Atlas. The mission revealed detailed relationships between these moons and the ring system within which they sat, which also confirmed a long-standing theory about the structure of the rings. At least the first 2 of these moons are shepherding moons, satellites that exist within the narrowest rings of Saturn and play an essential role in keeping the delicate structures in place by their gravitational interactions with the billions of particles within the rings. With its wide and narrow-angle cameras, Voyager 1 was able to take a series of pictures showing in incredible detail Prometheus acting as a shepherding moon to the F ring and Atlas as a shepherd to the A ring. This first Voyager craft was also sent by the team at NASA's Jet Propulsion Laboratory to investigate one of Saturn's most intriguing moons up close for the very first time. Titan had already been identified as potentially the only moon in the solar system with a thick Earth-like atmosphere, and Voyager was set on a course that enabled it to pass by within just 6,400 kilometers of its surface. As it flew on the dark side of the moon, looking back at Titan's atmosphere through the haloed light of the sun, it was able to accurately measure for the first time the density, composition, and temperature of the atmosphere, and also obtain a precise measurement of Titan's mass. This mysterious moon, the largest of all Saturn's satellites, was found to have an atmosphere almost entirely composed of nitrogen, just like the Earth, with a surface pressure just 1.6 times that of our planet. Voyager opened our eyes to this curious world for the first time, a world we would come to explore in even more detail with the Cassini-Huygens mission, which would touch down on the surface of Titan. As well as exploring the rings and moon systems of Saturn, Voyager 1 was able to deploy its array of sensors and cameras on the planet itself. With its closest approach on the 12th of November 1980, Voyager came within 77,000 miles of the Saturnian cloud tops, and was able to measure powerful winds traveling at 1,100 miles per hour, whipping around the planet's equator and aurora. But most intriguing of all was the discovery that Saturn's upper atmosphere was composed of only 7% helium, while the rest was mostly made up of hydrogen. Scientists had expected Saturn to have the same atmospheric helium levels as Jupiter and the Sun at 11%. So this much lower level suggested something intriguing was going on deep within Saturn's internal structures. Where was the missing helium? The lower levels in Saturn's upper atmosphere suggested that the heavier helium might be slowly sinking through Saturn's hydrogen. But it would take the arrival of Voyager 1's sister craft 9 months later to enable scientists to further probe the inner workings of Saturn and to begin to reveal the fate of the rocky ice world that had been lost inside this planet billions of years earlier. While passing behind Saturn, and so shielded from the view of the Earth, Voyager 2 used its radio science system to probe Saturn's upper atmosphere, gathering information on its atmospheric temperature and density. It was an ingenious dual use of its telecommunications system that allowed Voyager to create a temperature profile of the planet that provided the first direct evidence of something that scientists had long suspected. At the uppermost level of its atmosphere, Saturn's temperature was 70 K, minus 203 degrees C, while at the deepest levels, around 120 kilopascals, the temperature increased to 143 K, minus 130 C. Saturn, it seemed, was emanating far more heat than it was receiving from the Sun. This was a planet with a mystery at its heart, but Voyager was about to gain an even more beguiling insight into Saturn's inner workings. In August 1981, as the Voyager 2 probe passed over the north pole of the planet, it took a series of images with its 2 camera imaging systems that would reveal an extraordinary secret sitting on Saturn's crown. Stitching together the images and analyzing the data from this distant probe, David Godfrey and a team from the National Optical Astronomy Observatories in Tucson, Arizona, were able to piece together a startling image of a storm system, unlike anything ever seen anywhere in the solar system. First published in 1988, 7 years after Voyager 2 had left the Saturnian system, the patchwork image revealed a puzzling, hexagon-shaped weather pattern sitting around the planet's northern pole. Each of the 6 sides of this vast storm system is around 14,500 kilometers in length, 29,000 kilometers across, and at least 300 kilometers high. It's so vast, the Earth could fit into it at least 4 times over. And it's not just the scale of it that's breathtaking. Swirling inside it are winds whipping around at speeds of over 320 kilometers per hour, and the whole hexagonal storm is completely rotating every 10 hours and 39 minutes. This is a storm on an unimaginable scale, and 30 years later, it still rages on. But despite multiple hypotheses, the atmospheric dynamics behind its shape remain a mystery. As the seasons changed and spring arrived in the northern hemisphere towards the second half of the mission, we got the chance to look at the hexagon that surrounds Saturn's pole. If you flattened it out, it would be about 2 Earths wide. Saturn itself is about 10 Earths wide. So this is a major feature, and it's basically a jet stream. Every time we posted a picture of the hexagon on our website, the hits went through the roof, because I think people were so amazed that you could have something in an atmosphere that had straight sides to it. Carolyn Porco, Cassini mission. From our vantage point here on Earth, it looks as if our atmosphere stretches on and out forever, and yet, by the most widely held definition, it takes a journey of just 100 kilometers to officially make your way through the atmosphere and into space. Of course, atmospheres don't just stop dead. The Earth's atmosphere gradually recedes with increasing altitude, becoming progressively thinner, until by the time you get 100 kilometers up, you'll have 99.999997% of the atmosphere below you. This essentially arbitrary line between the Earth and space is known as the Kármán line. It's a line that was calculated by the Hungarian-American engineer and physicist Theodor von Kármán to be the altitude at which the air becomes simply too thin to support aeronautical flight, where, as he wrote, aerodynamics stops and astronautics begin. Cross this line, and you have officially gone from being a pilot to an astronaut. And you get to join a club that still only contains 561 members at the time of writing. The number of humans who have made it over the line is still so small, because travelling the short hop into space might be slight in distance, but it is large in terms of the power and technology needed to lift anyone or anything that far from the Earth's surface. Gravity binds us tight to our little rock, and despite over 60 years of space travel, it means almost all of us are still very much rooted to the ground. One of the reasons why the rings have captivated us for so long is that despite their vast distance from the Earth, if you look through a simple telescope, they shine back at us, bright against the night sky, reflecting the sun's light as powerfully as the planet itself. For years, the age and origin of the rings has been argued over, with conflicting evidence supporting two very different hypotheses. On one side, the argument has been made that a ring system as dense as Saturn's must be an ancient structure shaped from the remnants of the planet's formation. On the other side of the fence, the evidence has been used to suggest that the rings must be youthful, a relatively recent addition to the ancient planet. The brightness of the rings is not only beautiful but also rather surprising. The solar system is not a very clean place. In fact, it's full of dust and dirt, and so we would expect any ice crystals that hang around for any length of time to inevitably get dirty. We also know that if ice gets dirty, it doesn't reflect sunlight anywhere near as brightly. So in the case of the rings, we would have expected, if they had been present over the lifetime of the planet, all of those particles and blocks of ice would have become increasingly less reflective. If they had formed anywhere near the birth of Saturn, they would almost certainly be invisible to us now, or at least incredibly faint. And yet they shine brightly, as if they were made just days ago. Mercury, the smallest of the planets and closest to the Sun, lost its atmosphere long ago, with only the merest wisps remaining today. Next there is Earth, sitting in the Goldilocks glow of the Sun. We have clung on to our 100 kilometers of atmosphere in one form or another for billions of years, allowing life to thrive under its warming embrace. Venus, on the other hand, despite starting with an atmosphere likely very similar to our own, has now choked on the 250-kilometer deep toxic atmosphere that blankets its surface today. Each of the four rocky worlds has seen its atmosphere ebb and flow over time. But no matter what twists and turns the story of each planet may have taken, there has always been, and will always be, a limit to the size that any atmosphere can grow around these relatively small lumps of rock. Before we return to Saturn to understand how its atmosphere grew in a very different way to those of the rocky planets, we should take a swift look through the history of the Earth's atmosphere in more detail to establish how it began and evolved. Using a combination of geology, climatology, and paleontology, scientists have been able to piece together an immensely detailed picture of the Earth's atmospheric evolution. Far back in the Earth's history, a very different type of atmosphere to the one we see today surrounded the primordial planet. The newly formed Earth had grabbed onto gases from the billowing vapors of the solar nebula, the cloud of gas and dust that the planet had formed from, consisting almost entirely of hydrogen and simple hydrogen-based molecules such as water, H2O, methane, CH4, and ammonia, NH3. This primary atmosphere would have been entirely created by the capture of the nebula's gases by the gravitational attraction of the planet. Slowly, over time, the composition of the atmosphere changed from a hydrogen-based one to one rich in nitrogen and carbon dioxide. We think this shift to the secondary atmosphere was at first triggered by the giant impact of the planetesimal Theia on the early Earth, and then driven by a combination of gases produced during the late heavy bombardment, while asteroids rained down on our planet for millions of years, and the geological activity within the Earth sent vast quantities of gas upwards through all-encompassing periods of volcanism. By the time first life appeared on the planet, the nitrogen-rich atmosphere was stable. But gradually, as life took hold, a new component would begin to appear in the Earth's atmosphere. 2.5 billion years ago, photosynthetic life had become so prevalent, it triggered a tipping point known as the Great Oxygenation Event, during which oxygen was produced by living things at such a rapid rate, it far exceeded the amount of oxygen that was captured from the atmosphere in Earth's geological chemical reactions. The result of this shift to the third atmosphere has been the presence of free oxygen in our atmosphere ever since, providing the energetics to support the rapid evolution of life on Earth. And of course, one of these life forms has become so dominant we've developed a way of life that is now fundamentally changing the atmosphere of our planet for a fourth time, but not for good. Now, with this history of our planet's atmospheric evolution in mind, let's return to the earliest days of the solar system and explore the very different path taken by Saturn. Around 4.5 billion years ago, the young Saturn had grown to become one of the largest rocky bodies in the history of the solar system. At least 10 times the mass of the Earth, it found itself far beyond the warmth of the Sun, locked in its icy orbit, a frozen, rocky world on a scale unlike anything we've ever seen. But time would not stand still for this world. Having grown as large as it could from rock and ice alone, its barren surface would not stay lit by the dim light of the Sun for long. As it continued to grow, Saturn would become a radically different kind of planet, defined not by its rocky surface, but by an atmosphere that would bury it beneath vast volumes of gas. An atmosphere that would not just enwrap the planet, but engulf it. Just like the Earth in its earliest days, as Saturn continued to grow, it drew not just solid material but also gas towards it, from the vast clouds swirling around the embryonic solar system. Huge amounts of the hydrogen and helium left over from the formation of the Sun clung to the vast planet, creating a first atmosphere that may well have been very similar to the earliest one on Earth. But Saturn's early atmosphere would follow a very different course, as it was driven by two key differences between the young worlds. First, Saturn had grown far, far bigger than Earth, so by gravitational attraction alone, the volume of gas it could attract towards itself was far greater than anything the diminutive Earth was able to. But it wasn't just size that drove Saturn's atmosphere to grow so rapidly. Located this far from the Sun, the freezing temperatures meant that even the most volatile of gases could cling on to the planet without being driven off by the heat of the Sun. Hydrogen, helium, ammonia, methane, and many other gases that were too light for the smaller worlds of the inner solar system to hold on to, were able to accumulate out here, with Saturn's vast mass and the freezing temperatures being enough to draw them in. Trillions upon trillions of tons of gas began to envelop the planet, reaching depths first of hundreds of kilometers and then thousands. And as this new atmosphere grew, it transformed the surfaces below. On Earth, under our canopy of air, it's easy to forget that all of those molecules sitting above your head right now have a weight. If you draw a 1 centimeter square on a piece of paper, at sea level, and imagine a column of air stretching all the way up from the square to the top of the atmosphere, it will have a mass of, on average, just over 1 kilogram, exerting a downwards force of 10 newtons onto the paper, a pressure that we call 100 kilopascals, or 1 bar. That might not sound like much, but all of that weight reveals itself in the subtle and not so subtle effects of atmospheric pressure that we can see all around us. For example, the simplest of classroom experiments can reveal the power of the atmosphere by the process of just removing the air from a plastic bottle. The bottle collapses, not because of the vacuum that it creates, but because the bottle cannot withstand the pressure of the atmosphere that is pushing down on it. While 100 kilometers of atmospheric pressure can quickly crush a bottle here on Earth, a much bigger atmosphere can exert pressures that not only are able to shape things on the surface, but also have the power to transform an entire planet. And that's exactly what we think happened to Saturn 4.5 billion years ago. As its atmosphere deepened, the thousands upon thousands of kilometers of gas weighing down on its surface began to generate incredible pressure, heating the rock and ice so much they began to glow. It's thought perhaps that for a brief moment in time, the heat generated on the surface of Saturn by these extraordinary pressures meant that the glow of the planet even outshone the Sun. But this was just the beginning. As Saturn matured, the pressure at its core grew to 10 million times the level we experience on Earth. At that level of pressure, matter behaves in extremely strange ways, and the very idea of a planetary surface becomes meaningless. As Saturn took on its new form, the enormous pressures generated crushed and melted its solid core, destroying the rocky world it had been and replacing it with a new world, utterly alien in its characteristics. Saturn had transformed from a world of rock and ice into a wholly different class of planet, a gas giant, a ball of gas so big it could contain 800 Earth-sized worlds inside it, making it the second largest planet in the solar system after Jupiter. At 7:55 and 46 seconds AM Eastern Daylight Time on the 15th of September 2017, NASA's Deep Space Network antenna complex in Canberra, Australia, received notification that contact had been lost with one of our greatest space explorers. After 13 years of extraordinary encounters, the Cassini spacecraft had made its last fateful maneuver, plunging headfirst into the atmosphere of Saturn. 45 seconds later, the craft would be gone, crushed by the atmosphere of the planet it had spent over a decade so carefully exploring. Its last image, a monochrome view of the planet's night side lit by the reflected light of the rings, was a picture of its own grave, revealing the location towards which the spacecraft would plummet in its final act of self-destruction as it entered the planet's atmosphere just a few hours later. This was the end of a 20-year mission that had exceeded all expectations. The fourth spacecraft to enter the Saturnian system, following after Pioneer and the Voyagers, Cassini was the first to live there, ultimately spending 13 years and 76 days in orbit around Saturn. During this time, it explored the planet, its rings and its moons, and relayed images and information in a level of detail that would change our understanding not just of the Saturnian system, but of the whole solar system and our place within it. It all began on the 15th of October 1997 at Cape Canaveral, with the launch of the spacecraft aboard a mighty Titan IV rocket. To get to this moment had taken the best part of 15 years, the combined efforts of 28 countries, and a budget of $3.26 billion. But even then, it would be another 7 years before Cassini could truly begin its mission objectives. Getting this 5.5-ton machine across 1.6 billion kilometers of space would require a complex trajectory that would take it on 2 flybys of Venus and out to the asteroid belt, before returning to the Earth 2 years after takeoff for a final slingshot from its home planet that would send the craft hurtling at speeds of 98,346 miles per hour, outwards past Jupiter and on towards its final destination. This complex and high-risk trajectory was designed to exploit the orbital momentum of Venus, Earth and Jupiter to enable the spacecraft to accelerate, which helped keep the amount of fuel and hence the launch weight to a minimum, while making sure the craft could pick up enough speed to complete its epic journey. However, the trade-off of using this VVEJGA, Venus-Venus-Earth-Jupiter gravity assist trajectory, was a nervous 6-year, 261-day wait for the team back on Earth, as the craft made its convoluted voyage across space. Primary voyage complete, Cassini now faced the life-or-death challenge of slowing itself down with enough precision to enter orbit around Saturn. The tiniest miscalculation would have seen billions of dollars flung into the outer reaches of the solar system and decades of work lost forever. On the 30th of June 2004, the spacecraft began its complex Saturn orbital insertion, SOI, maneuver, by flying through the gap between the F and G rings. This maneuver alone was not without serious risk from the potentially devastating impact of particles in the rings colliding with the craft, so Cassini had to carefully orient itself to protect its instrumentation. Once through the ring plane, the spacecraft had to rotate itself once again to point its engine directly along its flight path, so that when the engine fired, it would decelerate the craft by a precise velocity, 622 meters per second, allowing it to fall into the gravitational hand of Saturn. Decelerate too much, and the craft would fall into Saturn. Too little, and it would fly off into outer space. At 8:54 p.m. PDT, Cassini was finally captured by the gravity of this gas giant, becoming the first spacecraft to ever orbit Saturn. A new age of exploration had begun. And over the next 13 years, Cassini would provide an extraordinary return on investment. The Voyagers and Pioneer had given us our first rough glimpses of Saturn's moons, but during its 13 years in orbit round the planet, Cassini did so much more. Not only did it discover a whole host of new moons, it also helped solve countless mysteries around moons we already knew existed, such as Titan and Enceladus, and revealed just how varied the characteristics of the 60-plus moons of Saturn really are. Cassini also allowed us to study for the very first time the interactions between Saturn's menagerie of moons and the ring system within which they sit, as well as the structure and history of the ring system itself. One of Cassini's key mission objectives was to explore the characteristics and activity of the vast atmosphere that makes up most of Saturn. Voyager 2 had revealed the presence of a heat source buried deep beneath the planet's cloud tops that seemed to be producing vast amounts more energy, up to 87% more, in fact, than the planet absorbs from sunlight. But what was the source of this heat? And how did Saturn's immense atmosphere organize itself into the vast and intricate weather systems like the huge hexagon? This remained a question that Cassini was charged with solving. Atmospheres can be some of the most spectacular and complex environments found on any planet. From the crushing intensity of Venus's choking atmosphere with its raging winds and sulfuric acid rain, to the thin blue line of Earth, where even on our somewhat milder planet we see endless storm systems. In the inner solar system, the atmospheres of the rocky planets and the weather systems they contain are all powered by a single source, the relentless heat of the sun. All the weather we see on the rocky planets, whether it's a dust storm on Mars or a hurricane on Earth, are driven by the same simple process. It begins with the sun beating down onto the planet's surface, heating the ground, which in turn radiates back, heating up the air closest to the ground. That air expands, which means it becomes less dense, and so the hot air closest to the ground rises. The result of all this rising air is that you get thermals, energetic movement of air from the ground into the upper atmosphere. Over the oceans, exactly the same process occurs, with the heat of the sun evaporating vast amounts of water and lifting it up into the atmosphere. So, in the very simplest terms, all of the extraordinary weather we see on Earth, or any of the other terrestrial planets, is driven by the sun heating the land and sea and causing the air to move around. Travel further out into the solar system, however, and the character of any atmosphere radically changes. The storms on Saturn are among the most violent found anywhere in the solar system. Generated by rich, complex and powerful weather systems, we've been witnessing these giant storms from afar for almost 150 years. Asaph Hall, the great American astronomer and discoverer of the two moons of Mars, was the first to observe one of these storm systems back in 1876. Looking through the largest refracting telescope of the time, the United States Naval Observatory's 66-centimeter telescope located in Washington, D.C., he was able to make out a great white spot sitting in the northern hemisphere of the planet. At the time, Hall wouldn't have known much at all about the phenomenon he was looking at. It was intriguing simply because it enabled him to make the first estimate of the rotational period of the planet. Over the following decades, however, this great white spot was observed again and again, roughly falling into an appearance every 20 to 30 years before slowly fading away. Fortunately for us, the long gaps between each appearance were cut short in December 2010, when a great white spot appeared just 4 years after the previous one. This time, with the Cassini probe in orbit, we had the opportunity to track the evolution of one of these storms close up from its birth in early December 2010 to its disappearance 8 months later. This vast storm system, resembling in many of its characteristics a simple thunderstorm here on Earth, emerged as a single white spot 1,300 kilometers from top to bottom and 2,500 kilometers from side to side. Over the ensuing months, Cassini was able to follow the storm as it stretched out around the planet. Just a few weeks after its formation, the tail of the storm had extended across 100,000 kilometers. And within 6 months, this great storm had stretched so far, it encircled the whole planet. Cassini was able to image directly for the first time lightning occurring in the middle of this giant storm in broad daylight. The fact that the lightning could be detected on the day side of the planet surprised the Cassini team and suggested that the lightning must be particularly intense to make it visible in such bright light. The lightning flashes are comparable to the strongest lightning flashes that we see on Earth. That was a joy, just to finally witness lightning on Saturn. And we could tell that it was coming from the cloud layer, the deepest cloud layer, which is about 60 miles down, and is the water cloud, the water ice cloud. And that makes sense because lightning is produced on Earth because of updrafts and particles being elevated through an atmosphere, rising through an atmosphere because they're convecting. We had a whole variety of scientific goals at Saturn, and one of the main ones was to understand the meteorology of the Saturn atmosphere and what energizes the winds that we see on it, and so on. And we have affirmed now the belief that the atmospheric systems on Saturn are actually powered by energy from below, from an internal source on Saturn. They're not powered by sunlight, like we have on Earth. Caroline Porco, Cassini mission. Cassini was also able to turn its cameras onto the giant hexagon structure that Voyager 2 had first photographed over 30 years before. This time, with its high-definition, narrow-angle cameras trained on the enormous feature around the North Pole of the planet, Cassini was able to capture the giant hurricane-like storm in extraordinary detail. This vast vortex was measured as 2,000 kilometers across at just the eye of the storm. And with cloud speeds traveling at over 150 meters per second, it's rotating far faster than any hurricane we've ever seen on Earth. Exactly what causes this or any of the giant storm systems we've witnessed on Saturn is still not fully understood. But one thing we absolutely do know is that this far out from the sun, these weather systems cannot be driven primarily by the sun's heat. With Saturn receiving 100 times less of the sun's energy than Earth, something else must be driving its weather, something that creates the same great upswellings of heat we see on Earth, but that on Saturn is entirely generated from the interior of the planet. As yet, we've not been able to peer deep enough into Saturn's interior to see directly what happens inside this strange world. But in the last couple of years, we've come closer than ever. As we've accumulated evidence from Pioneer, Voyager, and of course Cassini, and combined it with our increasingly sensitive ground-based observation, we've been able to start piecing together a detailed journey into the heart of the planet. By just touching the cloud tops of Saturn, alive with great storm systems and flickering with immense bolts of lightning, they have given us the first hints of the truly strange world that must lie beneath, and the mysterious energy source that brings this planet to life. Our journey deep into the interior of Saturn begins not with clouds, but with rain. At the very outer edges of its atmosphere, in the space between the closest ring, the D ring, and the planet itself, we've discovered the phenomenon of ring rain, an endless downpouring of material falling from the rings into the upper atmosphere of the planet below. We know this because as Cassini took its final fatal plunge on the 15th of September 2017, it flew through this uncharted no-man's land and was able to make the first direct measurements of the rain falling from the rings. Using the ion and neutron mass spectrometer, it measured the rate at which the rain was falling from the rings, a staggering 10,000 kilograms of material every second. It was also able to reveal that the ring rain is comprised of a mix of hydrogen, water ice, and a surprising quantity of complex organic compounds like butane and propane, all showering down onto the planet and changing the chemistry of its upper atmosphere in ways we are only just beginning to understand. Cassini then began its final historic dive into the upper atmosphere of Saturn, struggling to keep its antennae pointing towards the Earth as it was buffeted by the increasing turbulence, while continuing to send a stream of precious data back to us right until the very end. Traveling at around 123,000 kilometers per hour, Cassini entered Saturn's upper atmosphere at 3:30:50 PDT, 1,900 kilometers above the planet's cloud tops. This was the first time scientists had ever been able to sample the atmosphere directly, our distant human envoy touching the gas giant for the very first time. Over the next few seconds, Cassini increased the use of its altitude control thrusters to steady its rapid descent into the thin outer reaches of Saturn's atmosphere and keep the antennae pointing towards Earth for a final few seconds of contact. But this was a losing battle. Over the next minute and a half, the growing density of the upper atmosphere rapidly began to increase the friction on the forward-facing surfaces of the spacecraft, raising the temperature at high speed and creating an unfolding thermodynamic situation that Cassini had not been designed to withstand. At precisely 3:30 PDT, 1,500 kilometers above the cloud tops, Cassini finally lost its battle for control. After 20 years in space, 13 of which were spent exploring Saturn, and having traveled a distance of 7.9 billion kilometers, this battered explorer was no longer able to maintain a stable flight path through the increasingly dense atmosphere. Beginning to tumble and roll, the last few bytes of data left its antennae streaming the 90-minute journey back to Earth, and the mission was long over before that final contact reached our planet. Precisely what happened next to the little spacecraft as it fell into the grip of this giant planet remains no more than well-informed conjecture. Using computer models to predict its final seconds, the Cassini team were able to watch only in their mind's eye as the craft tumbled chaotically through the atmosphere. Traveling at 144,200 kilometers per hour, just 1,100 kilometers above the cloud tops, and with temperatures rapidly increasing, every component of this unprotected machine began to disintegrate. With all computer systems failing and the spacecraft blind and deaf to its surroundings, it began to break up, its gold insulation blanket rupturing first, before the external carbon fiber structures of the spacecraft itself began to fracture and fragment. Then, with the rings gleaming in the sky above it, and the yellow cloud tops beckoning below, what was left of Cassini streaked across the Saturnian sky, blazing with temperatures higher than the surface of the sun. The gas tanks of propellant that helped steer the craft on its epic voyage blasted apart the remaining structures into 1 million different pieces, which in a final spectacular moment lit up a little corner of the majestic planet with the burning debris of its greatest explorer. Cassini was dead, but its final journey was far from over. Over the following minutes, the debris scattered and fell through the cloud tops, deep into the planet's interior, until finally the atoms of this beloved machine, built by human hands millions of kilometers away on a faraway world, came to rest in the heart of the planet. Cassini and Saturn, inseparable forevermore. Where the debris of Cassini finally ended up, we can only imagine. But the data from this extraordinary mission that was collected right up to its very end has helped us to dive deeper into the detail of Saturn's interior than ever before. As the wreckage scattered and fell from the upper atmosphere, it would have fallen through the very first cloud tops of the planet. Here, with temperatures ranging from -170 to -110 degrees Celsius. The clouds are made not of water ice, but frozen ammonia. It's these ammonia ice crystals that give Saturn its characteristic pale yellow color, a color that we can see shining back at us with even the most modest of earthbound telescopes. Beyond this upper layer of cloud, as the pressures begin to increase and the temperature rises, huge clouds of water ice form a thick layer, the water molecules perhaps long-lost remnants of the building blocks of the icy world that Saturn once was. It's here, amongst the vast cloud systems, that lightning more powerful than anything we see on Earth illuminates the sky within storm systems that rage for months on end. Cassini gave us the first still and moving images of these lightning storms and enabled us to predict the next great transformation that will happen within the planet's interior. Every couple of decades, Saturn surprises us and breaks into a fit and actually erupts with really major storms. These are global storms, and they last for about 6 months to a year. The one that we saw with Cassini in 2010 was so powerful that our calculations show it was the most powerful storm we've ever seen anywhere in the solar system, even Jupiter, in terms of its central conductive storm system. We had an amazing chance to see that during the Cassini mission. And then when we looked at those clouds that it was forming, we found amazing things in the storm clouds of Saturn. We found that it had water ice. And this really blew our minds because water should be sequestered deep down in the atmosphere. You should not find it at the top of the atmosphere. It only gets there when you have huge convective updrafts, and we're talking updrafts that bring gas up from 100 miles down. And on the Earth, we only see gas going up and convection going up only about 10 miles. Here you have storms 10 times bigger, very powerful storms, lifting things up from 100 miles down and bringing up the water from below, which was probably actually a mixture of gas and water. But then it brought it up and it turned into ice, and the component of water ice in it really shocked us. Kevin Baines, Cassini mission. We now think that around 100 kilometers below the visible atmosphere, the same distance from the surface of Earth to space, with temperatures inside Saturn's lightning reaching almost 30,000 degrees Celsius, this lightning transforms methane gas in the atmosphere into huge clouds of carbon soot, carried higher into the atmosphere on great convection currents. We think that it's these specks of carbon-producing lightning that can explain the mysterious dark clouds that Cassini was able to observe and image over many years. This particulate matter rains down from the upper cloud layers until, at a depth of 1,500 kilometers, we think the enormous pressures begin compressing this soot into graphite, which then falls further into the depths of the planet. We then think that at around 6,000 kilometers down, this graphite undergoes a truly extraordinary transformation. With pressure and temperatures rapidly increasing, the graphite is compressed into solid diamond that rains down for at least 250,000 kilometers. Estimates suggest at any one time 10 million tons of diamond hail is raining down within the planet, from specks of diamond dust just a millimeter across to chunks as big as 10 centimeters. Perhaps even for a brief moment in time, some of the charred, carbonized remains of the Cassini probe made it down into these depths and transformed into diamonds as well, falling further into the planet it had helped us understand. But eventually, even these diamonds will ultimately succumb to the enormous pressures of Saturn's interior. Around 30,000 kilometers into the atmosphere, where temperatures reach 8,000 degrees Celsius, the diamond melts and forms liquid diamond raindrops that continue to descend into the abyss. It's here, around 40,000 kilometers down into Saturn's interior, that we believe the source of Saturn's energy, the energy that drives all the storms and weather we see playing out on its surface, is finally revealed. Here, the pressures are so intense that the hydrogen that makes up over 96% of Saturn's mass is compressed into a vast ocean of liquid hydrogen that is saturated with helium gas. Under these enormous temperatures and pressures, the helium precipitates out and falls like rain through the ocean, depleting the levels of helium in Saturn's outer layers, which explains the lower than expected amount of helium first measured by Voyager 1 in 1980. It's a process that, through the simple action of friction as the molten helium rain falls, creates an incredible amount of heat, and we think this is the engine, the energy source that helps power Saturn's ferocious weather and drives its entire atmosphere for tens of thousands of miles in every direction. Finally, we reach the interior of Saturn. a layer where the liquid hydrogen is so compressed it starts to behave like a liquid metal, and the helium itself may accumulate into a metallic shell surrounding the core. Beyond here, we do not know if a rocky core remains as a remnant of Saturn's long-lost past, or whether under these enormous pressures the possibility of solid rock is no longer viable. Whatever lies at the center of Saturn, we estimate that this core region has a mass of around 20 times that of the Earth, and a diameter of around 25,000 kilometers. And here, perhaps, a few tiny fragments of Cassini might have come to rest in the ancient heart of the planet. Saturn has lived a life of incredible drama. The evolution from rocky beginning to the extraordinary gas giant we see today took just a few 100 million years of rapid transformation. And yet throughout almost all of this time, one thing has been missing. We now think Saturn was born naked, and has lived out the vast majority of its existence without the structure that makes it more iconic than anything else. Saturn is a world defined by its rings. Ask a child to draw a planet, and more often than not they'll draw something that looks remarkably like Saturn. The particles in the rings of Saturn are almost impossibly delicate and intricate. Most of them are no bigger than snowflakes, but some are as large as houses, orbiting the planet at 1,800 kilometers per hour, in one of the most beautiful structures we have ever laid eyes on.